Hello students, so we'll see today the cylindrical waveguides. Okay, so here you can see actually the figure here. So this is the cylindrical shape you can see here, and with radius a. Okay, we are taking some arbitrary point, let's say. So the radius is defined here rho. Okay, and the azimuth angle is phi here, correct? And depending upon the propagation, we are assuming the z direction or minus z direction. Okay, so with respect to this geometry, actually we'll try to find it out, the different field component associated with this geometry, as well as the parameters like cutoff frequency, wave impedance, and the beta. Fine. So like you can see here, this cylindrical waveguide. Okay, particularly you can visualize as a hollow metallic pipe. Okay, with some radius a. Fine. So this kind of uh, geometry, okay, or the waveguide actually, okay, which is made of the single conductor, can support the TE or TM mode. TE or TM mode. I should say and, okay, TE and TM mode. Fine, because of the nature of the geometry is made of the single conductor. Fine. Now in a last class we have seen the generalized equations for the field equation in a cylindrical coordinate system for the different modes. Now in a continuation, actually we'll be opting a mode here first, maybe the TE or TM, and on it actually we'll be analyzing this cylindrical waveguide system. Fine. So let us begin actually. So we'll do here particularly for the TE mode first, and then we'll see the TM mode as well. So very first thing is that the longitudinal field component, okay, which is Hz here, okay, because the Ez component will be 0 for the TE mode. So this longitudinal field component must satisfy, okay, this, which is del square Hz plus k square Hz is equal 0. Fine. Now here this Hz is rho phi z, okay, is a longitudinal component, and we wrote like this: Hz is a function of rho phi e to the power minus j beta z. Fine. Okay. Now we supposed to see this equation del square Hz plus k square Hz is equal to 0. Likewise we did in cylindrical waveguide system as well, rectangular waveguide system as well actually. Now the thing is, we supposed to insert this Hz here. Hz is a function of rho pi in above equation, and we supposed to expand these things in a cylindrical coordinate systems too. Fine. So here you can see this del square Hz could be expressed, okay, in a cylindrical coordinate system. For your information, I can write here these things. So let's say we have this component, okay, and if you want to expand in a cylindrical coordinate system, so it will be like this: 1 upon rho dou dou f over dou rho plus 1 upon rho square dou square f and dou phi square plus, of course, the last component will be dou square f over dou z square. Fine. So we supposed to use this, okay, in this equation. Fine. Now, so let us expand this, and we'll be rewriting this equation in terms of the small hc. Fine. Now, so the moment you are inserting this hc is a function of rho phi, so it will look like this: dou square hc is rho phi over dou rho square plus 1 upon rho dou hc over dou rho phi dou rho plus 1 upon rho square dou square hc rho phi and dou pi square. Fine. Fine. What else? If you see, so we recall actually these things here, and if you see, the first term is fine, 1 upon rho dou over dou rho, and this one, so you're supposed to expand this actually. So the expansion of this actually written like this, okay, first two terms. The second terms you see here, which is 1 upon rho square dou square f over dou pi square, okay. So here you can see it is written as it is, these things, okay. We just replace in place of f to hc. Fine. Now the last term is that dou square f over dou z square. Fine. So here we supposed to recall hc, okay, the complete thing. So the moment actually you will recall these things, okay, so you will find that it is going to differentiate with respect to z. Fine. The last time I'm talking about. So basically this hc is a function of rho phi, okay, it will be constant for that, and e to the power j beta z will be differentiated twice, you know. So the moment you are differentiating that particular term twice, okay, so it will be what? Minus beta square, okay, hc is a function of rho phi. Considering that e to the power minus j beta z is going to be multiply in each term, correct? Fine. So this is one thing, plus, and the last term of the from the equation k square h z, which is function of rho and phi is equal 0. Fine. Now you see these two terms, which is k square minus beta square, is nothing but your kc square. Fine. So actually you can rewrite this equation once again, okay. So this term will remain same, so I can copy it, okay, and the last term will be plus this k square minus beta square, you can replace here with the kc square hc rho phi. Fine. And equal to 0. Fine. And kc square, you know, this is k square minus beta square. Fine. So now the magnetic field, this magnetic field function may be determined using the separation of variable technique. What is that? Separation of variable technique, okay. And for that actually we supposed to assume the solution in this form. What is that? hc is a function of rho phi. We can assume r is along the function of rho and the p along the function of phi. Fine. So this format will be utilizing further, okay, exploring the equations. Now, so what we are going to do actually, we are going to replace this hc, okay, hc, okay, with this. Fine. Now, so the moment you are replacing that thing, so the equation will be p is a function of phi Okay, and now here we'll be having the differentiation, not partial differentiation. We have the differentiation because we segregated like that. Okay, r rho over dou rho square plus p is a function of phi rho d r is a function of rho over d rho plus r rho. Hopefully you can manage it, these things. D square p phi. Just a minute, it's not looking perfect, so I can write once again d phi square, and of course the last term, which is kc square. R is a function of rho and p is a function of phi is equal 0. Now what we can do, actually, you see here this term is coming here, so we can divide with r and r into p, okay, in whole equations. Fine. So the moment you will divide with this equation with r into p, it will look like 1 upon r, the function of rho d square r rho over d rho square plus 1 upon rho r rho dr rho over. Now what you can see here, these equations is along the function of p or r, so it will be similarly, we will be approaching, okay, what we did in last time. We'll be considering a constant here, and accordingly we'll be writing the separate solution for r and p. Fine. So yes, so this is the third term would be 1 upon rho square, and this will be p is a function of phi, and d square p phi d phi square plus kc square is equal 0. Fine. Hopefully this is clear to all. Okay, so now here what you can see, actually, this equation, if you see, particularly this term, if you see, okay, what is that? This is along the function of the p, okay, or the function of phi. Fine. So we can equate to a constant term. Let us consider here minus k phi square. Fine. So how we can write this equation? Once again, d square p, the function of phi, is d phi square plus, okay, and we are equating to minus k square, so we may write k phi square p phi is equal 0. Hopefully it's fine. Okay, now, so if this is fine, so we may recall once again the solutions, okay, what we did actually in the last time, correct? So basically in place of this, okay, we consider this is minus k phi square, and then we have this equation. Fine. Now we can recall the general equation for this second order differential equation, and yes, we may write these things because we are writing actually this p and r, is basically defining the hc component. Okay, so the one general equation we may recall, this will be p, the function of phi, is equal a sine k phi plus b cos k phi phi. Okay, and here the function p, okay, this p actually, which is a function of phi, okay, must be the periodic in phi. Okay, so that what will happen, the k phi must be a integer, let's say n. Fine. So what we can do actually, in place of k phi phi, okay, or k phi you can replace with n. So the equation would become a sine n phi plus b cos n phi, like that. Okay, so this is one thing. Another is that, because let us go back once again to this equation, and in place of this actually we'll be writing, let's say, minus n square. Okay, fine, because this is integer, so let us define the n in terms of n. It is quite so popular with this, so writing, so in place of minus k phi square I'm replacing minus n square. Fine. So the moment when I'll do this, so yes, I may write rho square over r rho d square r rho over d rho square plus rho over r rho d the function of rho d rho plus rho square kc square, and then of course minus n square is equal to 0. Fine. Now the thing is, this is somewhat special, this differential is somewhat special, and this form of the differential equation is popularly known as Bessel's equation. Okay, and the solution known as the Bessel functions. Fine. So the general solution of this Bessel equation could be expressed like this, which is r. Here r actually, the function of rho is c times of jn. Okay, just a minute. And this argument will be kc rho plus dyn kc rho. Fine. Where these jn is the argument kc rho is actually the nth order Bessel function of the first kind. What is that? This is nth order Bessel function of first kind with argument kc rho, and this yn argument kc rho is the nth order Bessel function of second kind. Okay, so in a mathematics this is well explored actually already. Fine. So it will be really helpful, okay, to solve our cylindrical waveguide or the similar kind of the transmission lines. Fine. So let us see some of the aspect of the Bessel functions. Okay, maybe you may be aware these things. Okay, so let me just recall. Just a minute. Yes. So here what you can see actually, this is actually the jn, where this jn versus x. Fine. And x is the argument here. Fine. In a similar way what we wrote like kc rho is the argument there. Now here you see the jn 0 is a finite value, and basically this jn actually, if you see, so Yeah, so these are equations. Actually I can paste it here, just a minute. Okay, so this is one. Okay, what is that? It is defined like this: under root 2 by pi x cos x minus n pi by 2 minus pi by 4 when x is tending to infinity. Okay, if it's tending to infinity, you can calculate the gn like this, whereas if x is tending to 0, okay, if it is 0, so the equation will be different. Just a minute. Okay, so this is the equation in case of x is tending to 0. So you're supposed to calculate your this gn, which is a Bessel function of the first kind, with this. Fine. So this is one thing. So I'm especially talking about here. This is the gn, which is the first kind of the Bessel function. First kind of Bessel function. Fine. Now why this is important actually here, because mathematically we may have the several things, but here in our this problem, okay, what is acceptable, we're supposed to figure it out. Now let us see here the Bessel function, okay, of the second kind. Okay, so let me just paste. Okay, so here you can see this is what, this is yn, okay, which is actually the plot of the Bessel function, okay, of the second kind. Fine. Now here if you clearly see, actually for n is equal 0 or n is equal 1, okay, 2, and particularly if you see that n is equal to 0 when x is equal 0, okay, this is infinite, this is infinite. So that actually creates some issues here, and if you look into it, these things, so you can find the proper solutions for your cylindrical waveguide. How? I'll tell you these things, how this will work. So before that, I can give you some equations, maybe useful for you. Okay, so for your these things. So when x is tending to infinity, okay, this yn could be calculated from this equation, whereas when you have x is tending to 0, okay, then your yn could be calculated from this equation. Fine. Now the thing is, coming back to our problem, so let me write down, okay, the solution, okay, which is r is a function of rho is cjn, okay, is argument kc rho plus d yn kc rho. Fine. Now what it says actually, when you have the zero argument, okay, when you have the zero argument, the value is infinite. The moment this term is infinite, okay, so like this is physically not acceptable for our solution, okay, but what we can do actually, okay, so it means if we say, if you go at rho is equal to 0, okay, so the argument will be 0 and this will be infinity. Fine. Okay, and this will create some problem here. So then what should we do actually? It means that the constant here, this constant, what we can assume here, it should be 0. So it means d must be 0. Okay, so we left with this much only. Okay, so the solution will carries only the Bessel function of the first kind. Fine. So hopefully this is explanation is clear to all. It's very important. Okay, because at rho is equal 0, this is infinity, which is physically unacceptable for the circular waveguides, and that is why, okay, this constant must be 0. Now we wrote the solution for P, and now we have the solution for R. Let us multiply to get the Hz. So the Hz will be the function of rho phi. You are multiplying R rho and P phi. Fine. Now the moment you multiply, this is Jn Kc rho and A sine n phi plus B cos n phi. Fine. Okay. Now the overall Hz you may write like this: rho phi z is equal to Jn Kc rho A sine n phi plus B cos n phi e to the power minus j beta z. Okay, this is the overall the Hc, fine. So right now we have Hc here, and because if you recall from the last class, we can write down all the transverse component, because we see this transverse component in a longitudinal component. So yes, now we have the sufficient information to get the things, but before that let us talk about somewhat the boundary condition, because this is we are talking about the cylindrical waveguide system, which is made of the metal, okay, considering this time the PEC, perfect electric conductor. So here because we are talking about the T mode, definitely Ez is 0. Okay, so we left with the Hc, only the longitudinal component we have the Hc here. And if you can write the E phi component, okay, and particularly this E phi component on the surface of this cylindrical waveguide, okay, so in place of rho, if I write A, so means at the radius phi z is equal 0. Fine. Okay, so this is one of the boundary condition, you can say, okay, and could be utilized to fix the other things here. Okay, so let me recall sorry so let me recall this E phi, okay, in terms of the Hc. Actually we already derived last time, which is this relation dou Hc over dou rho, and this will be, okay, you're supposed to differentiate, okay, this equation, okay, this Hc with respect to rho. Fine. So basically when you are these things differentiating this one, okay, so you left these things with j omega mu over kc and j and dash. Okay, dash means this is a what we differentiated with respect to rho, actually, because the argument is like that. And basically in place of rho we are these things we are making a. So let us write down kca, and of course a sine n phi plus b cos n phi and e to the power minus j beta z, and this should be 0. fine, as per the boundary condition. Fine. So the TE mode of the cylindrical waveguide, okay, is going to be defined by, okay, when you have the Jn dash KCA become 0, okay, because at rho is equal A, okay, E phi is supposed to be 0. Fine. Hopefully this is clear to all. Now if we define here the mth 0 of the derivative of nth Bessel function, okay, as P and M dash, okay, then the cutoff wave number could be find as let me check, this is KCMN A is equal PNM dash, okay. Here you can see actually this PNM dash actually is a root of Jn dash, okay, KCA, okay. This is what? This is the root of this function. Fine. Hopefully this is clear to all. Fine. So in this way we can define like this, okay. So now we can write KCMN is equal PNM divided by A. Fine. Now the thing is, what I'm trying to say here, if you can see this plot, you know, let me copy. Okay, so if you see these things, so what we supposed to do, we supposed to make this Jn prime KCA supposed to be 0, okay. So yes, if you let's say if you are taking let's say n is equal 1, okay, so you will find 1 0 here, 1 0 here, of course 1 0 here, and others it is also true actually, for n is equal to 2, 1 0 here and 1 0 here, these things. So what we can write actually, this where you are getting the first 0, okay, of this Jn, okay. So let's say this is P prime n 1. Again for this one, this is P prime n 2, and similarly the third one is here, which is P prime n 3. Fine. So that is why I am saying here this is a mth 0 of the derivative of nth order Bessel function. Hopefully this is clear. So in journal we written like this, P prime n m. Fine. Okay. Now, so once this is fine actually, yes, we can calculate the cutoff frequencies, okay, these things. Now, so the transverse field component for the TEM mode could be written like this here, for TENM mode. Fine. So what is that? This is E rho phi G is equal minus J omega mu over Kc square rho dou Hc over dou phi. Fine. So if you differentiate with respect to phi, you will be getting J omega mu n over kc square rho jn kc rho, of course, a cos n phi minus b sin n phi and e to the power minus j beta z. So this is E rho. Fine. In a similar fashion, you can write E phi. Okay, so I can directly write j omega mu kc jn prime kc rho is the argument, and of course a sin n phi plus b cos n phi e to the power j beta z. Now we left with the two more, which is h rho is minus, you supposed to recall from the previous class what we derived for the TE mode, all the transverse component in terms of the HC. Fine. So the moment you are putting the HC there, you can find all the transverse component. It's so easy. So I hope you can find it, all the things. You please verify all the steps, expecting that you are verifying all the things what I'm writing. If anything, please let me know. A sin n phi plus b cos n phi e to the power minus j beta z. H phi is minus j beta n over kc square rho jn kc rho, and of course a sin n phi minus b sin, sorry, this is a cos n phi, fine, minus b sin n phi e to the power j beta z. Fine. So these are all the field components for the TE-NM mode. Fine. Now the cutoff frequency could be determined like this: kc nm is equal to pi fc nm under root mu epsilon is equal to p prime nm over a. Fine. It will define as fc nm is equal p nm prime, like this is what the we differentiated the Bessel function, and from there we got this thing. Hopefully this is, you may recall these things. Fine. This is what the cutoff frequency for the cylindrical waveguide in TM mode. So basically how we are determining these things: beta square is equal k square minus kc square. So the moment you want to find the cutoff frequency, so k is equal kc, you're supposed to make it, and then only you can get these things. The other things, maybe the wave number may be an important thing. So this is beta nm is, you can write in terms of the cutoff frequency, or in terms of the p prime, which is the root of that Bessel function. Yes, so I can write both, I believe. K square minus p prime nm over a square is equal k under root 1 minus fc nm over f to the whole square. This is one thing. Okay. Now what we left? Anyone? So another thing, I think we missing these things, the wave impedance, I believe. Okay. Yes, I think we are missing the wave impedance. So yeah, wave impedance for the TEMN mode is Z TENM is equal to E rho over H phi. This is k eta over beta, or you may write eta over under root 1 minus fc and m over f to the whole square. Okay, so this is all about the TEMN mode uh, for the cylindrical waveguide system. So let us check once again all the things. Okay, so how we started. So we started with the cylindrical waveguide for the TE mode, and this del square HC plus K square HC must be satisfied. Okay, and where HC we know, which is a longitudinal component multiplied with e to the power j beta z. Okay, so the moment we are satisfying this equation, writing in the cylindrical coordinate system with the help of this, correct, will give you this equation. And basically here if you see, the HC is a function of rho phi, and we're supposed to figure it out the solution of this differential equation. So we will be using the separation of variable technique and defining the HC in a new format, like R is a function of rho and P is a function of phi separately. The moment we are replacing this HC with R and P, okay, you will have this equation you can see here. And again we find that this equation is this differential equation is a function of alone R or P actually. So this term we are considering as a minus k phi square, writing this differential equation, and for the general solution is like that. And then after the moment we replace this k phi minus k phi square is minus n square. So this format is a very well known and popular format of the differential equation, popularly known as the Bessel equation. And for the Bessel equation we have what? This is the general solution where the Jn is the nth order of the Bessel function of the first kind, where the Yn is a this argument kc rho is called as the nth Bessel function of the second kind, you know. Then after we went through these Bessel functions, fine, okay, the first or second kind, and it was very important to note it down that the moment when you have the yn 0, which is the infinite, okay, which is not physically acceptable here, so for removing this, the constant d should be 0. And finally we arrived at the overall HC here. The moment we have the HG, yes, we can free to find it out all the transverse component, recalling previously derived component for the TE mode. But before that, that E phi, like at the periphery or at the radius, or the radius rho is equal a, this will be 0. So making this is 0, this E phi, and defining the other terms, the other roots actually. So here you can see this is Jn prime, okay, is Kc is equal to 0, and here this Pnm prime is actually basically the roots of this Jn prime Kca, fine. And this Jc and prime Kc actually, so these are actually the zeros you are getting, okay. So these are the roots, different roots. So defining this different root, making in a generalized solution as P prime and M, okay, fine. Now after defining this, we can define the other components, like other transverse component E phi, E rho, H phi, H rho, okay. And we defined here the cutoff frequencies, okay, the wave number and impedance, wave impedance, okay. So this is all about for the circular waveguide or cylindrical waveguide with TE mode. Now in a similar sense actually we can have the field components and other parameters for the TM mode. So we'll see those things in a next class, followed by the modes. We'll try to visualize the mode also. Thank you so much.